Beneath the dust of centuries lies evidence of a technological sophistication we are only beginning to understand. In tombs and ruins across the ancient world, archaeologists have uncovered tools that shouldn't exist. Devices of such precision and mechanical genius that their creators seem to possess knowledge that would only resurface centuries, even millennia later. From mystical weapons that could slice through falling silk to mechanical calculators that operated like modern computers, these devices represent the pinnacle of human ingenuity in the ancient world. If you find these mysteries as captivating as we do, and you appreciate deep explorations into history's greatest puzzles, please consider subscribing to this channel. We dive deeper into these unexplained mysteries every single week. Now, let us take you on a journey into 15 of the most extraordinary technological achievements ever created in the ancient world. Chapter 1. The Ulfberht Swords. Imagine standing on a medieval battlefield, where the clash of steel determines the fate of kingdoms. A warrior raises his blade, a legendary sword marked with a mysterious inscription, plus V L F B E R H T plus. This is no ordinary weapon. The blade catches the light, revealing a distinctive water-like pattern flowing across its surface. When it meets an enemy sword, something extraordinary happens. The inferior blade shatters. The Ulfberht blade remains unblemished. These legendary swords tell a story that connects us directly to one of history's most remarkable metallurgical achievements. The Ulfberht sword represents not just a weapon, but a peak of material science that wouldn't be equaled in Europe for nearly 1,000 years. Approximately 170 examples of these swords have been discovered, primarily scattered across northern Europe, dated to the 9th through 11th centuries. Each one bears the telltale inscription carved into its blade. The mystery of these blades begins with their performance. During an era when most European soldiers carried heavy, brittle iron weapons that would bend or snap under the stress of combat, the warriors who possessed Ulfberht swords carried something fundamentally different. These blades offered a perfect balance between hardness and flexibility. They could maintain a razor-sharp edge, yet absorb the shock of a cavalry charge without failing. When a master smith polished one of these weapons, the steel revealed an intricate swirling pattern, a visual signature that penetrated deep into the blade's molecular structure. For centuries, scholars assumed this pattern was purely decorative, perhaps an etching or surface treatment applied by a skilled artisan. It wasn't until the late 1990s that modern metallurgists using electron microscopy discovered the startling truth. The Ulfberht smiths had inadvertently engineered nanotechnology. Deep within the blade structure, researchers found evidence of carbon nanotubes and cementite, nanowires, microscopic structures that gave the steel its legendary strength. These dimensions were so small, approximately 1,000th the width of a human hair, that achieving them required a perfect understanding of temperature control, atmospheric conditions, and the precise combination of materials. The craftsmen who created these weapons were stationed in the southern regions of India, in areas like Tamil Nadu and the Deccan Plateau, where they operated what amounted to the world's first industrial complex dedicated to steel production. These were not simple blacksmiths. They were chemical engineers, centuries ahead of their time. The production method these ancient metallurgists developed was called the crucible process. Iron ore of exceptionally high purity was sealed inside small clay vessels alongside specific organic materials. Charred wood and the leaves of a particular plant species called cassia. Once sealed completely with clay, these crucibles were placed into furnaces and heated for several days in a carefully controlled environment. By sealing the crucible, The Smiths created a pressurized, oxygen-free environment. This allowed the iron to slowly absorb carbon from the charred plant matter in a precise, measurable way. The result was a high-carbon alloy of such purity that modern industrial sensors struggle to match it. What made this technique even more remarkable was that the specific plants and ore deposits used in this process contained natural trace elements, particularly vanadium, which acted as chemical catalysts, allowing the nanostructures to form in precise parallel bands. The Ulfberht swords served a specific military purpose. The South Indian empires that produced them were naval and land superpowers, requiring weapons capable of withstanding prolonged, high-intensity warfare. Some of their elite warriors wielded a weapon called the Urumi, a flexible whipsword that demanded steel capable of being coiled and repeatedly flexed without breaking. Only the unique nanostructure of Ulfberht steel could survive that mechanical stress. The combination of hard carbides and a softer, flexible matrix gave their best regiments an advantage that was both psychological and practical. In wars of attrition, their blades could effectively outlast the weapons of their enemies. The global demand for this material became so immense that one of history's greatest scientific failures was eventually born from it. In the early 1800s, the renowned British physicist Michael Faraday, the man who pioneered our understanding of electromagnetism, became obsessed with replicating the Ulfberht steel. He obtained original samples and attempted to reverse engineer the process in his laboratory. Despite his genius, Faraday could not unlock the secret. He suspected the key lay in adding silica or aluminum, but his replicas lacked both the distinctive water pattern and the internal strength of the originals. He eventually abandoned the project, leaving the mystery unsolved. It wasn't until modern analysis that researchers finally discovered why Faraday and countless others had failed. The true secret wasn't just in the carbon content or the heat. It was embedded in the earth itself. The iron ore found in the Deccan Plateau contained natural trace amounts of vanadium, a rare element essential for forming the cementite nanowires in parallel bands. Without that specific geological fingerprint, even if you possessed the correct recipe and technique, the method would fail. The ancient Smiths had developed a technology perfectly calibrated to the unique chemistry of their local soil. Chapter 2. The Dioptra. In the bustling port city of Alexandria, during the 2nd century BCE, a Greek engineer named Hero designed an instrument so sophisticated that it would not be duplicated in precision for nearly 2,000 years. The dioptra, a name that literally means sighting tube, represented a quantum leap in surveying technology. Unlike the simple tools his predecessors had relied upon, Hero's creation combined the principles of geometry, astronomy, and mechanical precision to enable measurements of angles and distances with an accuracy that would astound Roman engineers. The dioptra was born from a fundamental challenge. In an age before computers and electronic instruments, how could engineers establish precise measurements across vast distances? How could they accurately survey terrain, plan military installations, or ensure that aqueducts maintained the exact gradient necessary for water to flow downhill at a constant, reliable rate? The answer lay in a device that embodied sophisticated mechanical engineering principles. The instrument consisted of a rotating graduated circle, often marked with precise angular measurements. 2 sighting vanes, visual guides positioned at specific angles, allowed an operator to align the device on distant objects. Unlike earlier surveying tools that relied primarily on gravity and crude visual estimation, the dioptra incorporated precision screws that could be adjusted with remarkable fineness. An operator could rotate and tilt the instrument using these mechanisms, allowing for alignment on distant points with an accuracy that was, for its time, almost miraculous. What separated the dioptra from simpler surveying instruments was its versatility. It could measure angles not just in horizontal planes, but also in vertical planes. This made it invaluable for calculating the gradients necessary for water engineering projects. Work that demanded precision within fractions of a percent. When Roman engineers needed to construct massive aqueduct systems, some of which stretched for tens of miles and needed to maintain a consistent downward slope of often less than 1%, the dioptra became an essential tool. The mechanics of the device relied on principles that would later be refined and improved over centuries. Operator would position the dioptra at a reference point and use the graduated circle and sighting vanes to observe a distant landmark. By recording the angle and comparing it to readings taken from other known positions, surveyors could triangulate distances and heights with impressive accuracy. The precision screws allowed for adjustments of remarkable fineness, sometimes to fractions of a degree. There were limitations to the dioptra, and Hero himself understood them. The instrument was complex, expensive to manufacture, and required a skilled operator who had undergone specialized training. For general surveying tasks, simpler tools like the GROMA, which we will explore in our next chapter, were often preferred. However, whenever maximum precision was required, whenever engineers needed to establish the layout of a military camp with exact measurements or calculate the precise gradient for an aqueduct system, the dioptra was the tool they turned to. The Roman military recognized the value of this instrument. Specialized surveyors, called agrimensor in Latin, carried the dioptra into the field during campaigns. These men were essential to the military machine. An army on the move required fortifications and camps that needed to be laid out with geometric precision. The dioptra made this possible. By projecting straight lines and precise right angles onto the ground, these surveyors could efficiently organize military engineering efforts. Beyond the battlefield, the dioptra's application in water engineering cannot be overstated. The Roman Empire's aqueduct system was one of its greatest achievements, but it was an achievement that required constant geometric vigilance. Water does not flow uphill. It must be coaxed downhill through carefully calculated gradients. Too steep, and the water moves with such force that it erodes the channels and causes damage. Too shallow, and the water stagnates and fails to reach its destination. The dioptra allowed engineers to maintain these critical gradients with precision that, measured by modern standards, was remarkably accurate. Remarkably, though ancient texts give us detailed descriptions of the dioptra, no original examples have been discovered. We know it existed through the writings of several ancient engineers and mathematicians. Hero of Alexandria described it in meticulous technical detail. The Byzantine scholar, Anonymous Byzantinus, wrote about it. The Arab mathematician Al-Karaji referenced its principles. Yet the physical artifact remains elusive. What we do know is that the principles embodied in the dioptra, the use of precision adjustment mechanisms, the application of graduated circles for angular measurement, the ability to take readings in both horizontal and vertical planes. These principles eventually led to the development of the theodolite, an instrument that would dominate surveying from the 16th century onward. In many ways, everything that surveyors do today traces a direct lineage back to Hero of Alexandria's ingenious design. As we move from the theoretical precision of the dioptra to the more practical surveying challenges that Roman engineers faced, we turn our attention to a simpler, yet equally ingenious tool, one that became almost the trademark of the Roman surveyor himself. Chapter 3. The GROMA, Among all the tools associated with the Roman Empire, few are as iconic as the Groma. While emperors commanded legions and architects designed monuments, the Groma symbolized the practical engineering precision that allowed Rome to organize space itself, to divide land into rectangular plots, to establish the geometric foundations of cities, to lay out military camps that could be recreated with identical precision wherever the army marched. The Groma is elegantly simple in design, almost deceptively so. At its heart was a rotating horizontal cross constructed of wood or metal, with a plumb bob hanging from each of its four ends. Beneath this cross was a vertical pole, called the ferramentum, which served as the reference point. The offset design was crucial. The cross was not mounted directly atop the vertical pole. Instead, it was positioned to the side, offset by means of a bracket. This seemingly minor detail was critical to its function. The purpose of this offset was to prevent the shadow of the vertical pole from interfering with sightings. When a surveyor looked along the lines created by the cross and the plumb bobs, they needed an unobstructed view. The offset design solved this problem elegantly. By positioning the reference point to the side, the surveyor could sight along the crossarms without obstruction. The Groma's function was specifically designed for establishing right angles and straight lines. When a Roman surveyor needed to lay out the grid of a new city, or to divide land into rectangular plots for distribution to colonists, or to establish the geometric foundation of a military installation, the Groma was the tool that made precision possible. The surveyor would position the Groma at a starting point, then align it on distant markers. Using the plumb bobs as reference points, they could establish a straight line and right angles with remarkable accuracy. The mechanism was brilliantly practical. A second person, called the poleman, would carry a ranging pole, a long wooden stake with markings. The surveyor would align this pole using the lines created by the crossarms. By moving from point to point, the surveyor could establish a geometric grid across the landscape. One of the most famous examples of this surveying work is the centuriation system used throughout the Roman Empire. The division of land into rectangular plots of standardized size, each centered around the Cardo and Decumanus, the two main survey lines that ran north-south and east-west. The Groma has an ancient history that predates Rome itself. The tool likely originated in Greece or Egypt, eventually being adopted and refined by Roman surveyors. The Greek name gnomon was the source of the Latin Groma, though it's unclear exactly which meaning was being referenced. What's certain is that by the Roman period, the Groma had become so associated with surveyors that it appeared on gravestones as a symbol of their profession, stylized in art, as a simple cross viewed from above, often with a vertical pole through its center. For many years, archaeologists only knew about the Groma through these artistic representations and written descriptions. The cross shown on gravestones, viewed from above, led to a misunderstanding about the tool's actual physical structure. Some scholars imagined it as a table-like device with the cross attached directly to the top of the vertical pole. This remained the prevailing interpretation until a remarkable discovery in Pompeii in 1912, when a complete Groma was excavated from the volcanic ash that had buried the city nearly 2,000 years earlier. The Pompeii specimen confirmed what the written descriptions had suggested. The Groma consisted of a vertical pole, called the ferramentum, with two supporting legs joined to the main pole by two diagonal rods. These diagonal rods contained carved notches. When the vertical position was correct, when the plumb bobs hung straight down, the notches on opposite sides would align. This alignment served as a visual confirmation that the instrument was level and properly positioned. The Groma was the democratizer of precision. Unlike the dioptra, which required significant training and was expensive to produce. The groma could be made by any competent carpenter. The design was straightforward. It required no complex mechanisms, no precision screws, no graduated circles. Yet it was capable of establishing straight lines and right angles across the landscape, with precision that was sufficient for most surveying tasks. The advantages became apparent when you consider the scale of Roman engineering. Across an empire that eventually stretched from Britain to the Euphrates, surveyors using the groma established the grids for hundreds of cities. The streets of these cities, laid out at right angles, followed the same geometric principles. The dimensions were consistent: 20 feet wide for major streets, narrower for secondary streets. The result was that a Roman citizen could travel from Britain to Egypt and find cities laid out according to the same geometric principles. But the groma's most important application may have been in military engineering. When the Roman army established a camp, what the Romans called a castra, precision was paramount. A temporary camp needed to be laid out quickly, but with enough geometric consistency that soldiers could navigate it in darkness, and that supply lines could be established with efficiency. The groma made this possible. Using the tool, surveyors could establish the geometric foundations of a military installation in a matter of hours. The legacy of the groma extends far beyond the Roman period. The principles it embodied, that measuring instruments should be simple, reliable, and capable of being understood and maintained by non-specialist operators. These principles influence surveying practices for centuries. Even modern surveying, though it now relies on electronic instruments and GPS positioning, still uses many of the same fundamental techniques that the Romans developed using the groma. As Rome's empire eventually fragmented, and as the geographic knowledge of the groma faded, the tool itself largely disappeared from use. Medieval surveyors would eventually develop new instruments and techniques, but the fundamental insight remained: that precision could be achieved through simple mechanical principles, and that such precision was essential to both military organization and civilian administration. Chapter 4. The Chorobates. Picture an engineer standing beside a long wooden beam, checking its alignment. The beam extends 6 meters, roughly 20 feet, supported by 2 vertical legs. The engineer holds a small string attached to a weight at each end of the beam. If those strings, hanging straight down due to gravity, align with specific notches carved into the supporting legs, then the beam is level. This is the chorobates, perhaps one of the most elegant, water-based leveling instruments ever created in the ancient world. The chorobates was specifically designed for one of the most critical tasks in Roman engineering: establishing perfectly level surfaces or precise gradients. The tool appears in the architectural treatises of Vitruvius, the famous Roman architect and engineer who documented the technical knowledge of his time. Vitruvius describes in meticulous detail how the chorobates was constructed and how it was used to measure horizontal planes, a task that was absolutely essential when constructing Roman aqueducts. The basics principle of the chorobates is deceptively simple, relying on one of nature's most reliable constants: gravity. A string or cord with a weight attached will always hang vertically. If 2 such strings are hung from opposite ends of a horizontal beam, and if both strings align with predetermined marks, then the beam itself must be perfectly horizontal. This is the foundation of the chorobate's design. The instrument consisted of a wooden beam of substantial dimensions. Vitruvius specified 20 Roman feet in length, which would be approximately 6 meters in modern measurement. This beam was supported by 2 legs. These legs were connected to the main beam through 2 diagonal rods, each of which contained a series of carved notches. When the beam was at the correct level, The plumb lines would align with specific notches on both the left and right sides of the beam. What makes the chorobates ingenious is that it provided a backup system for situations where the primary plumb line method might be unreliable. On top of the beam, Vitruvius describes a groove or channel carved into the wood. In conditions where the plumb bobs might swing due to wind or vibrations, making it difficult to determine their true alignment, a surveyor could pour water into this groove. Water, like a hanging weight, obeys the principle of gravity. If the beam was truly level, the water would remain stationary within the groove. If there was even a slight incline, the water would immediately flow toward the downhill side, revealing where the slope was. This water level principle was particularly valuable in field conditions where the wind or ground vibrations might affect a hanging plumb bob. The water would provide a definitive answer, level or not level. It was a redundant system, a built-in check that enhanced the reliability of the instrument. This redundancy in design, building in multiple verification methods, reflects a sophisticated understanding of practical engineering. Roman engineers determined that the ideal gradient for an aqueduct was remarkably precise, approximately 0.15 to 0.30%. This means that for every 100 meters of distance, the water level would drop only 15 to 30 centimeters. Achieving and maintaining such a precise gradient over distances that often exceeded 30 kilometers, sometimes over 60 kilometers, required measurements of extraordinary accuracy. This is where the chorobates became indispensable. The construction of the famous Pont du Gard aqueduct in Gaul, modern-day France, is a testament to the effectiveness of Roman surveying techniques using instruments like the chorobates. The aqueduct, which still stands today, maintained its gradient over a distance of approximately 50 kilometers, with such precision that water continued to flow properly for nearly 2,000 years. This was not luck. It was the result of meticulous surveying using tools like the chorobates. The process of surveying for an aqueduct using the chorobates was labor-intensive and required extreme patience. The surveyor would position the chorobates on one segment of the proposed water line. If the two plumb bobs aligned with their corresponding notches, or if the water poured into the groove remained level, then that section was properly positioned. The surveyor would move to the next position, typically separated by about 40 Roman feet, roughly 12 meters, and repeat the process. Each measurement would be recorded. Over the course of surveying a route of 30 or 60 kilometers, thousands of individual measurements would be taken. These measurements would then be compared and analyzed to establish the overall profile of the terrain. From this profile, the engineers could determine where the water channel needed to be raised above ground level on arches, where it could be buried beneath the earth, and where it needed to be carried through or cut through hillsides. What's remarkable is that modern measurements of Roman aqueducts confirm that this ancient surveying methodology achieved results comparable to modern instruments. Modern engineers measuring the Pont du Gard found that the Roman gradient, achieved with tools like the chorobates, was accurate to within a few centimeters over the entire distance. This is precision that would be difficult to achieve even with contemporary instruments. Yet the Romans achieved it over 2,000 years ago, using water and gravity. Chapter 5. The Sakia. Imagine standing beside a well that descends 50 feet into the earth. There is no pump. There is no electric motor. Yet water continuously flows upward, transported from the depths to the surface where farmers can distribute it across their fields. The mechanism making this possible is an elegant device called the Sakia, also known as the Persian wheel, though its true origins remain hotly debated among historians and archaeologists across 3 continents. The Sakia emerged around the 3rd century BCE, appearing in ancient Egypt, Persia, India, and eventually spreading across the Middle East, North Africa, and into medieval Spain. Unlike the Noria, which we will examine next, the Sakya does not rely on flowing water. Instead, it harnesses animal power: oxen, donkeys, horses, or camels that walk in circles. Their steady motion converted through gears and mechanical linkages into the upward movement of water from wells. The brilliance of the Sakya lies in its mechanical design. The system consists of two wheels, positioned at right angles to each other. A horizontal wheel, sometimes called the gear wheel, is turned by an animal walking in a circle. This horizontal rotation is converted into vertical rotation through a clever arrangement of gears and shafts. The vertical wheel, positioned directly above the well, features buckets or clay pots attached around its circumference. As this wheel rotates, the buckets dip into the water below and rise upward, spilling their contents into a collection channel that distributes water where it's needed. The mechanism using lantern gears, also called cage gears, was particularly ingenious for its simplicity and durability. These gears consisted of wooden rods arranged in a circle and pegged into wooden discs. Unlike solid pinion gears with precision-cut teeth, lantern gears could be constructed using basic tools. The teeth weren't formed by cutting or milling. Rather, they were simply wooden rods that could be adjusted or replaced as wear occurred. If dirt fell into the mechanism, it would pass through the gaps between the rods, rather than becoming trapped and jamming the system. The Sakya represented a significant technological leap in irrigation capability. While a single shaduf, the simpler hand-operated device, could irrigate perhaps 0.1 hectares in a day, a Sakya powered by 2 oxen could service multiple times that area. This multiplication of effort through animal power meant that fewer workers could manage larger agricultural operations. In regions with inadequate river flow for Nereus, the Sakya provided an alternative solution to the perennial challenge of water scarcity. The historical distribution of Sakya technology tells a fascinating story. Records suggest that at one point, approximately 25,000 Persian wheels were in operation simultaneously in India's Kolar district alone. Throughout Egypt, the Sakya became so ubiquitous in rural irrigation that it was considered the standard tool for well-based water extraction. In the Iberian Peninsula, Islamic agricultural communities integrated the Sakya into their sophisticated irrigation networks. The device appears in paintings, manuscripts, and archaeological contexts scattered across 5 continents. The social impact of the Sakya extended beyond simple agricultural productivity. In many communities, the operation of a Sakya required multiple family members, coordinating the animal handler, the bucket, manager, and the water distributor. This created a kind of shared labor that strengthened community bonds. In Islamic communities, the Sakya also served a spiritual function. Its constant motion served as a meditation aid, and the reliable supply of water enabled the ritual ablutions required by Islamic law. Despite its effectiveness, the Sakya eventually succumbed to mechanization. By the 20th century, electric pumps offered greater efficiency and required less labor. The majority of Sakya installations were dismantled or abandoned as rural electrification reached agricultural regions. However, in many areas of India, Egypt, and Southeast Asia, isolated examples still operate, maintained by families who have kept the knowledge alive across generations. The Sakya exemplifies a crucial principle of ancient engineering: that ingenious mechanical solutions could be created using locally available materials and minimal industrial infrastructure. A Sakya could be built by a skilled carpenter using wood, bronze, and clay. It required no centralized manufacturing, no supply chains for precision parts, no written technical manuals. The knowledge passed from master to apprentice, embedded in practical experience. As animal-powered water devices gave way to river-powered systems, we encounter an equally transformative technology. Chapter 6. The Noria Picture. The Orontes River in medieval Syria, with the city of Hama rising on its banks. Along the waterway, massive wooden wheels, some reaching up to 20 meters in diameter, turn slowly and steadily, powered entirely by the river's flow. These are norias, and they represent a different approach to an ancient problem. They do not require animals. They do not demand human labor. Instead, they harness the kinetic energy of flowing water to lift water to heights that would otherwise be impossible to reach. The noria, from the Arabic word for wheel, is documented as early as the 4th century BCE. The Roman Indian author Lucretius, writing in the 1st century BCE, described them with admiration. Wheels on rivers are constructed. Round their circumference are fixed paddles, which, when acted upon by the force of the current, drive the wheel round, receive the water in the buckets, and carry it to the top. His description captures the elegance of the mechanism perfectly. The design of a noria is deceptively simple. Large paddles or buckets are attached around the circumference of a massive wooden wheel. When the wheel is positioned in a flowing river, the water current pushes against these paddles with constant force. This resistance causes the wheel to rotate. As the wheel turns, the buckets attached to its rim dip into the river below, scoop up water, and carry it upward. When each bucket reaches the top of the rotation, it tips, spilling water into a collection channel that diverts it into aqueducts for city supply or agricultural irrigation. What makes the noria extraordinary is the sheer volume of water it can move. A well-designed noria, operating in a strong current, can lift more than 50,000 gallons per hour to heights exceeding 80 feet. This capacity allowed ancient engineers to overcome a fundamental limitation. The distance water could be transported via gravity-fed channels. Previously, irrigation was limited to land adjacent to riverbanks. With the noria, water could be lifted into aqueducts that transported it across miles of landscape, transforming entire regions from arid to fertile. The noria's most famous historical examples stand in Hama, Syria, where at least 16 of these monumental wheels still survive, some dating back to the 13th or 14th century CE. These wheels became so iconic that they inspired poetry, featured in local mythology, and were considered the defining visual symbol of the city. At their peak, more than 50 functional norias operated along the Orontes River in the Hama region. The construction of a functional noria required tremendous engineering expertise. The wheel needed to be balanced perfectly, or vibration and friction would prevent it from rotating. The buckets needed to be precisely angled to scoop water effectively, yet not be so deep that excessive water weight would slow the rotation. The axle needed to be strong enough to withstand the tremendous forces exerted by the water and the weight of the buckets. Every component had to work in harmony with the others. One of the remarkable aspects of noria engineering was its compatibility with aqueduct systems. A single noria could feed multiple aqueducts at different elevations. In Hama, archaeological evidence shows that pairs of norias sometimes operated simultaneously, each lifting water to a separate elevation. This allowed for more sophisticated water distribution networks that could service multiple communities or agricultural zones. The decline of the noria came suddenly in the early 20th century with the introduction of electric pumps. Where a noria required constant maintenance, careful positioning, and skilled mechanics to operate, an electric pump could be installed almost anywhere with access to electrical power. The efficiency gains were significant, the labor savings enormous. By mid-century, most of the Norayas that had served civilizations for 2,000 years had been abandoned. Yet the Noria remains one of humanity's most elegant engineering solutions to a universal problem: transporting water against gravity. It asked nothing of humanity except the understanding of how to work with nature's forces. Chapter 7. The Shaduf. The earliest evidence of the Shaduf appears on a cylindrical seal from ancient Mesopotamia, dating to approximately 2200 BCE. Some scholars argue it may have originated even earlier, possibly in India or Mesopotamia, developed independently by people facing the same problem: how to lift water efficiently from a river or well to irrigate nearby fields. Regardless of its birthplace, the Shaduf represents perhaps the most elegant solution to water lifting ever invented. So simple that a child can understand it, yet so effective that it has remained in use for 5,000 years. The Shaduf consists of a long pole balanced on a pivot point, like a seesaw. A bucket or scoop is attached to one end, the longer end using rope. On the opposite, shorter end, a counterweight is attached. The operator pulls down on the bucket end, which dips into the water source below. Once the bucket is filled, the counterweight automatically provides mechanical advantage, lifting the water upward. The operator then releases, allowing the bucket to swing up, and tips it, spilling the water into a collection channel. The mechanism works so efficiently because it leverages the principle of mechanical advantage. By making one arm of the lever significantly longer than the other, the operator can lift a comparatively heavy bucket with less effort. Any operator of average strength can repeatedly lift and lower a full bucket throughout an entire day without exhaustion. Children can participate in the process. The task distributes work across multiple people efficiently. One container of water lifted via Shaduf requires roughly 15 seconds of work. A single unit can therefore irrigate approximately 0.1 hectares, about 1/4 acre, in a 12-hour working day. While this might seem modest compared to mechanical alternatives, for small-scale agriculture and domestic water supply, it was often sufficient. Many communities built multiple Shadufs in series, stacked vertically, allowing water to be lifted progressively higher. In Egypt, tomb paintings from the 18th dynasty show scenes of 2 or 3 Shadufs arranged in sequence, with water lifted from the Nile to progressively higher elevations. The Shaduf appears in Egyptian art extensively, suggesting it was well integrated into daily life by the time of the New Kingdom. Pharaonic records and tomb paintings document the tool's use in both temples and agricultural settings. Some evidence suggests the Egyptians may have been the primary developers of the technology, though the debate continues among scholars. The design has never fundamentally changed because it cannot be improved without adding complexity that would outweigh the benefits. A modern Shaduf made today operates on the identical principles as one created 3,000 years ago. The bucket might be rubber instead of leather. The rope might be synthetic rather than plant fiber, but the mechanism is unchanged. This is the mark of perfect design. It requires no revision because there is nothing to revise. Perhaps most remarkably, the Shaduf has never become completely obsolete. In rural areas throughout India, Pakistan, Egypt, Sudan, and parts of Europe, Shadufs continue to operate today, many tended by the same families for generations. They require no fuel, no electricity, no replacement parts beyond rope. They operate silently. They can be constructed from materials available locally. They integrate the operator into the irrigation process, creating awareness of water conservation through direct physical participation. Chapter 8. The Gastrophetes. In the arsenal of an ancient Greek city, perhaps around the 4th century BCE, something extraordinary existed. A handheld weapon that would not be surpassed in design until the medieval period, 2,000 years in the future. The Gastrophetes, a name meaning belly shooter in ancient Greek, was unlike any bow that had come before it. It was the world's first true crossbow, and it represented a fundamental shift in how military power could be concentrated and deployed. The Gastrophetes was powered by a composite bow made from multiple materials laminated together. A wooden core, a layer of horn on the belly facing the archer, and sinew backing the bow. This combination created a bow far more powerful than a simple wooden bow could be. Yet what made the Gastrophetes revolutionary was not just the bow itself, but the mechanism for spanning it, cocking it for firing. Unlike a standard handbow, which requires significant upper body strength to draw the bowstring, the Gastrophetes incorporated a slider mechanism with a trigger block similar to what would later appear in Roman mechanical catapults. The operator would push the loaded slider forward, engaging the fork onto the bowstring. To span or cock the weapon, the operator would rest the rounded rear stock against their belly and press down with body weight. The heavier the operator, the more power they could generate. This meant that a heavier person could span a more powerful bow than a lighter one could manage, making weight a military asset rather than a liability. Once spanned, the Gastrophetes could be held at the ready indefinitely. An arrow knocked on the slider could be fired instantly when a target presented itself. This was a crucial advantage over traditional handbows, which required continuous muscular tension to maintain the drawn position. A warrior with a Gastrophetes could wait in ambush, holding the weapon ready without fatigue accumulating. When combat required immediate fire, the weapon was prepared. The Greek author Heron of Alexandria, writing in the 1st century CE, provides our most detailed description of the Gastrophetes, drawing on earlier accounts by the engineer Ctesibius from the 3rd century BCE. Heron's technical treatise, called the Bellipoeika, describes both the weapon's construction and its method of operation with sufficient detail that modern craftspeople have successfully reconstructed functional examples. The range of the Gastrophetes remains debated, though modern reconstructions suggest effective range to perhaps 200 meters, with potential maximum range potentially exceeding that. The accuracy, however, was significantly compromised by the unusual firing position. Shooting from the hip, literally bracing the weapon at waist level, is ergonomically awkward by modern standards. Yet this was apparently the standard method. Medieval Europeans would not develop the shoulder stock concept until around 1500 CE, 2,000 years after the Gastrophetes was invented. The Gastrophetes served as the direct ancestor to later Greek and Roman artillery. As military technology evolved, the basic principles evident in the Gastrophetes, the slider mechanism, the trigger block, the concept of stored energy released by a trigger. These elements were scaled up and refined to create the great mechanical catapults that would dominate siege warfare for centuries. The Gastrophetes was the bridge between the handbow and industrial-scale artillery. Yet despite its sophistication, the Gastrophetes eventually disappeared. As more powerful torsion catapults were developed, handheld weapons became less militarily valuable. The knowledge of how to construct them faded. No intact examples have ever been discovered archaeologically. We know the Gastrophetes existed only through written descriptions and drawings that survived through copying and recopying across centuries. Chapter 9. The Polybolos. Imagine standing on a battlefield where an adversary wields a weapon unlike anything previously conceived in human warfare. A single operator loads wooden bolts into a magazine, a kind of magazine that holds a dozen or more projectiles. They crank a winch. Suddenly, arrows are not fired one at a time. They are fired in rapid succession, one after another, automatically feeding from the magazine, spanning, and releasing without the operator needing to do anything but maintain the mechanical motion. This weapon was called the Polybolos. The name literally means multi-thrower, and it was, in essence, the world's first machine gun, created nearly 2,000 years before the Industrial Revolution would make such things common. The Polybolos was invented by Dionysius of Alexandria, a Greek engineer working in the arsenal at Rhodes during the 3rd century BCE. Unlike the gastrophetes, which was a handheld weapon for individual warriors, the Polybolos was a sophisticated stationary platform weapon, a catapult with revolutionary firing mechanisms that represented a leap forward in mechanical complexity that wouldn't be matched for centuries. Our most detailed knowledge of the Polybolos comes from Philo of Byzantium, a Greek engineer and mathematician who lived between approximately 280 and 220 BCE. Philo encountered a weapon similar to the Polybolos and left a detailed technical description in his work, Bella Poetica, literally, on the manufacture of missiles. His descriptions are so precise that modern engineers have successfully reconstructed functioning models based on his specifications, confirming that his accounts are accurate. The fundamental innovation of the Polybolos was its chain drive system. Traditional catapults required manual cocking. Operators would physically pull back the bowstring, using mechanical advantage, position the projectile, and fire. The process was sequential and labor-intensive. The Polybolos transformed this through an ingenious arrangement of gears, chains, and mechanical linkages. A wooden hopper magazine held multiple bolts positioned over the mensa, the cradle that holds each bolt before firing. The mechanism operated through a flat link chain connected to a windlass, essentially a winch with a crank. When the operator turned the winch, the chain would move, driving the mensa, the slider mechanism, forward and backward in a coordinated sequence. At the forward position, a gravity-fed bolt dropped from the rotating magazine into the firing slot. At the rear position, a lug protruding from the mensa's supporting bracket would catch the bowstring, cocking the weapon. At the forward position again, a trigger mechanism would release the claw holding the string, firing the bolt. The entire cycle was coordinated through the rotation of a pentagonal gear, 5-sided prisms that acted as inverted gears to regulate the timing. The Polybolos could fire over and over, without manual intervention beyond rotating the winch. Early estimates, based on Philo's descriptions and modern reconstructions, suggest firing rates of perhaps 5 to 12 bolts per minute, a volume of fire that would be devastating in a siege context. A single operator could maintain this rate of fire indefinitely, provided the magazine remained stocked with bolts. The accuracy of the Polybolos was surprisingly effective for its time. Recent research examining wall damage at Pompeii suggests that the weapon may have been used during the Roman siege of the city in 89 BCE. Researchers discovered tight clusters of small square and diamond-shaped holes in the stone walls, patterns so precisely grouped that they suggest not random catapult impacts, but rather the repeated strikes of multiple projectiles, fired in rapid succession from a single source. The spacing and grouping of these holes match what modern reconstructions would produce from a Polybolos firing repeatedly at the same target area. Remarkably, the archaeological evidence suggests projectile impact velocities of approximately 109 meters per second, faster than an arrow from a modern crossbow. This velocity was achieved without electricity, without manufacturing precision tools, using only the mechanical advantage of torsion power and carefully engineered leverage. The specialized knowledge required to construct and maintain this weapon died with the craftspeople who built it. Later, siege weapons evolved differently, perhaps because the technical knowledge was lost or because the Romans developed alternative designs that proved more practical or easier to maintain. Chapter 10. The Pantograph. In a Renaissance workshop, a draftsman needs to create a scaled copy of an intricate map. The original is too large. The copy must be proportionally reduced. Before photographs, before photocopiers, before any electronic reproduction technology, there existed a mechanical solution of remarkable elegance. The operator would position a tracing stylus on the original drawing, while a second pen simultaneously moved in a parallel motion, creating an identical copy at any desired scale. This device was called the pantograph, and its origins trace directly back to the ancient Greek engineer, Hero of Alexandria, who described it in his work Mechanics, sometime in the 1st century AD. The pantograph operates on a principle of mechanical linkage that seems almost magical in its simplicity. The device consists of a movable framework of rigid rods connected by articulated joints, typically arranged to form interconnected parallelograms. 4 rods are arranged in a pattern where opposite rods remain parallel to each other. When the operator traces, the outline of an image with a pointed stylus attached to one joint, a pen attached to another joint traces an identical or proportionally scaled image. The mechanical principle underlying the pantograph is based on the properties of similar geometric figures. If the linkage is adjusted so that the ratio of distances from the fixed pivot point to the stylus versus the distance to the pen is set to a particular value, the pen will automatically trace a figure that is a scaled version of what the stylus traces. The beauty of this mechanism is that it is purely geometric. It requires no calculations, no measurements, no adjustments during operation. Once the ratio is set, the scaling happens automatically. Remarkably, despite being described by Hero in the 1st century AD, the pantograph did not become widely known or used until the early 17th century, when the Jesuit priest Christoph Scheiner independently invented the design. Scheiner demonstrated and wrote about the pantograph in 1631, calling it the pantometrograph. His publication sparked widespread interest in the device, and within decades, pantographs became standard tools for mapmakers, architects, engineers, and artists throughout Europe. The applications of the pantograph extended far beyond simple drawing. Engravers used pantographs with rotating cutting tools to reproduce engravings at different scales. Sculptors employed 3-dimensional versions to scale sculpture designs up or down. In the 19th century, the pantograph principle was adapted for milling machines, allowing a skilled machinist to create duplicate parts at scaled sizes by using a template as a guide, with a rotating cutter following the pantograph's movements. During the industrial age, pantograph machines became essential tools in manufacturing. A single master pattern could be used to create multiple copies, each at a different scale, without requiring separate skilled craftspeople to recreate the original design manually. This efficiency multiplied productivity and reduced the variation between copies that inevitably resulted from hand reproduction. The principle is so fundamental that it persists even in the digital age. Modern computer-aided design, CAD systems, use the same mathematical principle of proportional scaling that Hero described nearly 2,000 years ago. When you click a Scale by 50% button in any digital design program, you are using a principle embodied in Hero's ancient mechanical device. Chapter 11. The Trip Hammer. In the forges of ancient China, a revolutionary technology emerged that would transform metalworking from a labor-intensive craft into a mechanized process. The trip hammer, also called a tilt hammer or helve hammer, represented one of the most important technological breakthroughs in the history of metallurgy. A powered hammer that could perform the brutal, repetitive work that previously demanded dozens of skilled workers laboring for hours. The written descriptions of trip hammers appear in Chinese texts as early as the Han Dynasty, around 40 BCE, though some historians argue the technology may date back as far as the Zhou Dynasty, over 1,000 years earlier. The basic design of the trip hammer is deceptively simple. A massive hammerhead, often weighing dozens of kilograms, is attached to one end of a long wooden beam or lever, called a helve. This beam is balanced on a fulcrum, a pivot point. The other end of the beam features a series of catches or lugs, like teeth on a gear. A rotating shaft, powered by a water wheel, moves these catches in sequence. As the rotating shaft moves, each lug or catch strikes one of the stationary catches on the beam's end, lifting the hammer end into the air. When the shaft rotates past, the lug is released, and gravity pulls the massive hammerhead downward with tremendous force. This simple mechanism transformed metalworking. In a traditional forge, a smith would spend hours drawing out a bloom of iron, the raw product from a smelting furnace, into long bars of usable iron. This process demanded constant, repetitive hammering, often requiring 2 or 3 people working in careful coordination. With a trip hammer powered by water, a single operator could control the machinery by opening and closing water gates, adjusting the flow through the mill wheel to increase or decrease the striking rate. The hammering continued relentlessly, without fatigue, without loss of precision. The sophistication of trip hammer systems increased over centuries. By the Song Dynasty in medieval China, elaborate arrangements of multiple hammer batteries could be driven from a single large water wheel. Engineers like Du Yu, working in the 3rd century AD, developed systems with several shafts arranged to operate off one massive wheel, creating synchronized arrays of hammers, each striking in precise sequence. The coordination required advanced mechanical knowledge. The water wheels needed to be strong enough to withstand tremendous forces. The connecting shafts needed careful balance, and the timing mechanisms needed precision to prevent the machinery from destroying itself through violent harmonic resonance. The trip hammers spread across Eurasia demonstrates a pattern that emerges repeatedly in ancient and medieval technology. Effective solutions developed independently in multiple regions, then spread through trade and cultural contact. Greek sources mention trip hammers in the Hellenistic period. Roman engineering texts reference their use. Chinese texts document their evolution in exquisite detail. By the medieval period, trip hammers operated throughout Europe, from Spain to Eastern Europe, wherever water power could be harnessed. The decline of the trip hammer came with the Industrial Revolution. Steam-powered machinery eliminated dependence on water location and flow rates. Modern hydraulic and pneumatic systems replaced the cams and catches. Industrial forges adopted power hammers that could be controlled with precision that pure mechanical systems could never achieve. Yet the fundamental insight that human labor could be multiplied and extended through mechanical advantage applied to natural forces remains the foundational principle of mechanization itself. Chapter 12. The Chain Pump Picture. An ancient Babylonian or Egyptian worker positioned beside a well or river. Above them, a wooden wheel rotates slowly, powered either by the current of a river or by the steady motion of draft animals. Around the rim of this wheel runs an endless chain, like the chain on a modern bicycle, but larger, running through a wooden tube that extends upward. At intervals along the chain, Small circular discs are attached. As the wheel rotates, the chain moves through the tube. Water enters at the bottom of the tube, becomes trapped between successive discs in the moving chain, and is carried upward. At the top of the tube, the chain emerges from the water, and the confined water spills out into collection channels. This is the chain pump, one of the most efficient and versatile water lifting devices ever conceived. Evidence suggests the device existed in Babylon as early as 700 BCE, documented in ancient texts. Later, it spread throughout the Mediterranean, adopted by Egyptian engineers around 200 BCE, and mentioned in detail by both Philo of Byzantium in the 2nd century BCE, and by the Roman architect Vitruvius around 30 BCE. The device eventually reached China, where it was called the dragon backbone pump, becoming central to Chinese irrigation agriculture for over 2,000 years. The chain pump's elegance lies in its simplicity and efficiency. Unlike some water lifting devices that work by displacing large quantities of water, the chain pump works by trapping water in discrete volumes and carrying it upward. The seal between the moving discs and the tube wall is not perfect. Some water leaks backward, but the forward motion of the chain overcomes these losses, ensuring a steady stream of water flows upward regardless of occasional leakage. The discs themselves evolved in design over centuries. Early versions used clay pots or ceramic cups attached to the chain with rope or simple wooden fasteners. Later versions used wooden discs carved to fit snugly within the tube, minimizing water loss through leakage. Chinese versions used square-shaped paddles instead of circular discs, adapted to the rectangular troughs they traveled through. These variations demonstrate how craftspeople in different regions solved the same fundamental problem in slightly different ways, each solution shaped by local materials and manufacturing capabilities. Power sources for chain pumps varied depending on geography and available resources. In locations with strong river currents, the pump could be powered entirely by water flow, requiring no animal labor or human effort beyond initial construction and occasional maintenance. In regions where river flow was insufficient, chain pumps were turned by animals, oxen, horses, or donkeys, walking in circles, their rotational motion transmitted to the pump through gearing mechanisms. In some contexts, especially in China, chain pumps were operated by teams of humans using pedal-like devices, turning the wheel through coordinated physical effort. In China, the chain pump's design was eventually improved through the addition of the first crankshaft mechanism, a rotating shaft with an offset lobe that converts circular motion into reciprocating linear motion. This innovation, credited to Al-Jazari in the 13th century CE, allowed a single rotation to power multiple pumps or other machinery in synchronized sequence. The crankshaft itself became one of the foundation mechanisms of industrial machinery, yet its origins trace to these medieval improvements on the ancient chain pump. The chain pump declined gradually as electric-powered pumps became available in the 20th century. Farmers abandoned the technology in favor of machinery that required no ongoing maintenance of mechanisms and gears. Yet in regions without reliable electricity, or in applications where simplicity and durability matter more than speed, chain pumps continue to operate today, their designs largely unchanged from designs thousands of years old. Chapter 13. The Wind-Driven Organ. Hydraulis. In the amphitheaters of ancient Rome, crowds gathered for entertainment. As gladiators entered the arena, a sound emerged, loud, penetrating, and utterly unlike anything heard before. An enormous musical instrument, operated by hand pumps and water pressure. produced a continuous flood of sound that could be heard throughout the entire venue. This was the hydraulis, invented in the 3rd century BCE by Ctesibius of Alexandria, and it represents one of the earliest examples of automation and mechanical control in human history. The hydraulis was not merely a musical instrument, it was a marvel of engineering that combined principles of hydraulics, the pressure and movement of water, with the physics of sound production. To understand how revolutionary this device was, one must recognize that before the hydraulis, musical instruments were limited by human breath capacity. A human musician could only sustain a note as long as they could hold their breath. The hydraulis eliminated this limitation entirely through mechanical means. The basic design consisted of a wind chest, a chamber connected to rows of pipes positioned above it. This wind chest was connected to a conical reservoir filled with air. 1 or 2 hand pumps supplied air into this reservoir. The innovation that made the hydraulis unique was the water regulation system. The conical air reservoir was partially submerged in a large cistern filled with water. As air pressure inside the cone increased, the water level inside the cone rose, compressing the air within. This water column provided mechanical stability, maintaining steady air pressure regardless of how much air the pump supplied or how much air the pipes consumed. The sound produced by a well-maintained hydraulis was loud and penetrating, perfectly suited for the outdoor amphitheaters where it was typically used. A single hydraulis could fill an entire arena with sound. During gladiatorial contests, the hydraulis accompanied the action, creating an atmosphere of spectacle and drama. Some musical pieces became famous, passed down through performance until the knowledge of them was eventually lost. The technical sophistication of the hydraulis extended beyond mere sound production. The key mechanisms had to be precisely balanced so that musicians could depress them with light touch. No excessive force required. This balance was critical because an operator working through multiple pieces might otherwise suffer hand fatigue. The connection between keys and the sliding mechanisms controlling airflow had to be precisely calibrated so that pressure variations didn't affect the instrument's response. The hydraulis spread throughout the Roman Empire and remained in use for several centuries. However, by the 5th century CE, the instrument declined rapidly in the Western Empire. The reasons remain debated. Some sources suggest that as Christianity gained dominance, the hydraulis was banned from churches due to its association with pagan spectacles and gladiatorial contests. Others argue that the maintenance requirements became unsustainable as centralized authority fragmented. By contrast, in the Eastern Byzantine Empire, the hydraulis continued to be used. References in 9th century Arab writings confirm its ongoing existence. Eventually, the instrument was abandoned entirely in favor of simpler designs, using bellows rather than water pressure systems. Yet the fundamental concept that mechanical systems could regulate and control the production of sound became foundational to all mechanical organs that followed. Chapter 14. The Automata of Al-Jazari. In Baghdad, during the late 12th century, an engineer named Ismail al-Jazari created something that would not be equaled in sophistication until the dawn of the modern industrial age. A collection of mechanical devices so complex, so ingeniously designed, and so intricately controlled that they anticipated modern concepts of automation, programming, and mechanical engineering by nearly 800 years. In 1206, just before his death, Al-Jazari compiled a comprehensive illustrated manual documenting his inventions. The Book of Knowledge of Ingenious Mechanical Devices. Al-Jazari did not work in isolation. He inherited a long tradition of mechanical innovation. The earlier engineer Philo of Byzantium had described catapults and pumps. The Banu Musa brothers, Islamic scholars of the 9th century, had documented mechanical devices and water-powered systems. Yet Al-Jazari took these earlier innovations and pushed them to unprecedented levels of complexity and sophistication. His contributions included the creation of the first recorded crankshaft mechanism, a device that converts circular motion into reciprocating linear motion. The crankshaft itself became one of the most fundamental mechanisms in all industrial machinery. Every automobile engine, every pump driven by electric motors, every mechanical system that needs to convert rotating motion into back and forth motion relies on the crankshaft principle that Al-Jazari documented. Yet Al-Jazari incorporated the crankshaft not into simple pumps, but into elaborate automata, mechanical devices that performed complex sequences of actions without human intervention. Al-Jazari's designs also incorporated sophisticated control systems. He used float valves that responded to changes in water levels, enabling devices to switch between different operating modes automatically. He developed throttling valves that maintained constant water flow despite variations in water pressure. He created feedback mechanisms where the output of one stage controlled the input to the next stage, establishing principles of automatic control that wouldn't be formally developed as science until the 20th century. The sophistication of Al-Jazari's mechanical designs is evident in his twin-cylinder pump, which incorporated the crankshaft mechanism with two pistons operating in precise sequence. As one piston was drawing water into its cylinder, the other was pushing water out through a valve system. This alternating action eliminated the pulsations that would result from a single piston pump, producing steady, continuous water flow. Modern engineers recognized in Al-Jazari's design the fundamental principle of multi-cylinder engines, where multiple pistons firing in sequence smooth the power output of the system. Yet despite the sophistication of his designs and the comprehensiveness of his book, Al-Jazari's innovations were largely forgotten in the Islamic world after his death. When European engineers finally encountered similar mechanical principles centuries later, they developed them independently, often without knowledge of Al-Jazari's prior work. The mechanical tradition he established was overshadowed by the rise of other engineering schools, and eventually by the Industrial Revolution, which approached mechanical problems from fundamentally different mathematical and scientific foundations. Al-Jazari's legacy reminds us that innovation does not inevitably build continuously from the past. Knowledge can be lost. Exceptional individuals can advance technology beyond what the broader culture is prepared to sustain. Yet Al-Jazari's fundamental insights, that machines could be programmed, that automatic control systems were possible, that efficiency could be achieved through complex mechanical coordination, these insights proved so fundamental that they eventually were rediscovered and became the foundation of modern mechanical engineering. Chapter 15. The Parahipparion. From the perspective of paleontology, the Parahipparion is not a tool in the conventional sense. It is not an instrument crafted by human hands, nor a device designed to solve an engineering problem. Yet it appears on this list because it represents something profound about ancient achievement. A creature so perfectly adapted to its environment, so successful in its ecological role, that it dominated vast continents for millions of years before vanishing entirely, leaving behind only fossils as testament to its existence. The Parahipparion was a small, three-toed horse, roughly 1.4 meters tall at the shoulder, weighing between 100 and 200 kilograms, depending on the species. It lived approximately 10 to 2 million years ago, occupying grasslands and savanna environments across multiple continents. The Parahipparion represents a crucial, evolutionary step in the story of the horse family, the transition from browsing eating leaves from bushes and trees, to grazing on open grasslands. To understand this transition, one must recognize that it demanded not just a change in behavior, but fundamental changes in anatomy. Grazing horses required high-crowned teeth, teeth that could withstand millions of chewing strokes, grinding tough grass fibers without wearing down to the root. The Parahipparian had developed these specialized teeth, showing clear evidence of a diet dominated by grass. Yet it retained a crucial feature of earlier horses: 3 functional toes on each foot. The fossil record shows that Parahipparian species were extraordinarily successful. During the peak of their dominance in the Miocene epoch, roughly 8 to 5 million years ago, they were among the most numerous large animals on Earth. Fossil sites throughout North America, Europe, Asia, and Africa reveal abundant remains of Parahipparian. Paleontologists estimate that at some locations, Parahipparian remains constitute the majority of all large mammal fossils discovered. This abundance was not accidental. The Parahipparian was a mixed feeder, capable of consuming both grass and browsing vegetation. This dietary flexibility allowed it to survive in varying environments and adapt to changing climates. Its 3-toed foot structure provided advantages that a single-toed design might not offer: better weight distribution, improved maneuverability, and flexibility in changing directions. Climate cooling during the Pliocene epoch reduced the extent of grasslands, converting them gradually to steppes and deserts. The vegetation that Parahipparian had adapted to exploit became less abundant. Simultaneously, new predators evolved: larger, more efficient hunters that competed for prey or directly preyed upon horses. The emergence of monodactyl horses like Equus, ancestors of modern horses, may have provided direct competition, their single-hoof design perhaps more efficient in certain environments. The Parahipparian represents a cautionary tale embedded in ancient paleontology. A species can be overwhelmingly successful, dominating its environment for millions of years, yet still be vulnerable to extinction. Adaptations that make an organism successful in one environment may become liabilities when that environment changes. The very specializations that allowed Parahipparian to thrive in its ecological niche made it inflexible when conditions shifted. Yet the Parahipparian was not a failure. Its lineage contributed to the evolutionary development of modern horses. Its fossils reveal details about ancient climates, ancient plants, and the structure of ancient ecosystems. In death, it teaches us about life. In the span of this exploration, we have journeyed through 15 extraordinary technologies. These 15 tools remind us that human ingenuity has always reached beyond what seemed possible. And they remind us that the most important technology is the one we might lose: the knowledge itself. Thank you for joining us on this exploration into history's greatest mysteries. If you appreciated this deep dive into ancient technology and innovation, please subscribe to our channel. We examine mysteries and unexplained phenomena from human history every single week. Until next time, keep exploring.